Okay, so now we're on to lecture 9 on series, still in sections 11.2 of our calculus textbook, which for those of you just turning in is Stewart calculus. We had in the last video talked about the fact that if the terms of a series do not go to 0, then the series necessarily diverges. However, we want to look at a specific example of a series here to show, it's an example that shows that the converse of that theorem is not true, meaning there are situations where the terms go to 0, but the series still diverges, meaning that the only thing we can say about a series by looking at the limit of their terms is if it does not go to 0, it diverges. But if it does go to 0, it may converge or diverge. We don't know. And this is the harmonic series, my favorite series. Classic series. If you're into music, it comes from the harmonics. I don't know enough about it to tell you much, but anyway, the series is 1 over I equals 1 to infinity. Of course, where we start from, as long as it's bigger than 0, it doesn't matter, because whether or not it converges or diverges doesn't really have much to do with where we start from, but the terms of the series themselves. So let's list a series. When I equals 1, we get 1. When I equals 2, we get 1/2. When I equals 3, we get 1/3. When I equals 4, we get 1/4, and so on down the road, right? This is the harmonic series. So this is a really odd series because let me list it out really in a lot of detail. So 1/3 plus 1/4, and I'm going to do 1/5 plus 1/6 plus 1/7 plus 1/8. And we're going to go on here, but let's just look at this. 3 plus 1/3 plus 1/4. The thing to notice is that 1/3 is bigger than 1/4, right? Because you're dividing by something smaller. So this whole thing is bigger than 1/4 plus 1/4. That little pair, 1/3 plus 1/4, is bigger than 1/4 plus 1/4, which of course is equal to 2/4, which is equal to 1/2. Now let's look over here at this next 4 terms, not 2 terms, but next 4 terms. Well, the smallest of these 4 terms is going to be 1/8, right? Because that's dividing by the biggest number. That's going to be the smallest. So that entire sum, those 4 terms, add up to something bigger than 1/8 plus 1/8 plus 1/8 plus 1/8, which of course is 4/8 or 1/2. So if I add those 4 terms, I get bigger than 1/8. Let's go out again. Let's go 1/9 plus 1/10 plus 1/11 plus 1/12 plus 1/13 plus 1/14 plus 1/15 plus 1/16. How many terms do we have here? We have 8 terms, right? 1, 2, 3, 4, 5, 6, 7, 8. All of them bigger than or equal to 1/16. In fact, all but one bigger than 1/16. So this is bigger than 8 times 1/16, which is, again, 1/2. So we got this is bigger than 1/2, this is bigger than 1/2, this is bigger than 1/2. And then what am I going to do again? Well, I'm going to go from 1/17 to what? Yeah, the next power of 2, 1/32. And how many terms are we going to have here? We're going to have a total of 16 terms here. And all of them, except for one, bigger than 1/32. 16 times 1/32 is, again, 1/2. So what's happening here? The thing is whatever this sums to, it's got to be bigger than 1 plus 1/2 plus, because of this term here, 1/2, because of these next 4 terms here, 1/2, plus because of the next 8 terms there, 1/2, plus because of the next 16 terms there, 1/2, because of the next 32 terms there, 1/2. It's going to be bigger than 1 plus 1/2 plus 1/2 plus 1/2 plus 1/2 plus 1/2, adding 1/2 to itself over and over and over again. And guess what? This does not converge. This goes to infinity. This diverges. I can get as big as I want by adding 1/2 to itself over and over and over again. And the idea is I keep going to the next power of 2 up, and I'm always going to have a next power of 2 up. It's an infinite series. So I'm, from 17 to 32 gives me 6. That's going to be bigger than 16 times 132. From 33 to what? 64. 1 over 33 plus dot, 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 all the way up to plus 1 over 64 is going to be bigger than 32 times 64, which is 1/2 again. You're going to be able to keep doing this, and you're going off to infinity. So this is a classic example of a series which diverges. It's got a bunch of other cool things, but we don't need to go there now. But for now, you just have to realize the terms go to 0. 1 over I does go to 0. Let me just make an emphasis of that. 1 over I goes to 0, but the series still diverges. This is to prove that the converse of the test for divergence is not true.